we're going to look at yet another lemma, and I guess I'm going to read you the statement and then kind of explain, what the takeaway is, right? Hopefully this gets us a little bit more insight into these stationary distributions, and then we'll get to practice with writing proofs. So first, what's the lemma about? So we start with this collection of one-step transition probabilities, the pxy's there, and we're also told that there's a stationary distribution, right? So one thing, kind of the reason for writing it this way, not to even mention the Markov chain, is to kind of highlight 2 points, right? One is that the stationary, anytime somebody asks you to find the stationary distribution, you should say with respect to which transition probabilities. And in other words, right, with respect to what Markov chain, right? So, anytime, the definition of the stationary distribution really always involves one-step transition probabilities, right, through this, through the global balance equations. And anytime you see one-step transition probabilities, you can immediately assume that there's some time homogeneous Markov chain that sort of is moving around somewhere up there. So right, that's what we're given, right? So we're not actually, I'm not actually mentioning the Markov chain X anywhere, but it exists somewhere. And the next thing we're asked to suppose is that there is some function alpha such that the limit of the k-step transition probabilities is equal to alpha y for every single starting point x. And so let's think about what this is trying to kind of communicate. But first of all, we know what the k-step transition probabilities are. Maybe it's worth to kind of give a little bit of a side note, right? But we know the one step, right? That's the probability of going from x to y in one step, and the k-step is going from x to y in k steps. And just maybe, I guess, to relate this to what you've seen in 160A, and I'm sure you've seen transition matrices, and in those terms the k-step transition probabilities were powers of the transition matrix. And I'm not writing it this way here, mostly because we're pretty often interested in state spaces that are not finite, right? So a transition matrix for Markov chain is a matrix where the xth row, right, where px, or I guess the entry pxy would be in the xth row and the yth column. And if s is infinite, like say if the state space is all integers, right, that's an infinite thing, and so your transition matrix now has an infinite number of rows and columns. And talking about the k-step transition probability is then a little bit strange, right? Because you would have to raise an infinite sized matrix to the kth power, right? So it's a little bit kind of a strange thing to do. So that's basically the reason for this choice of writing the k-step transition probability this way. And in the case when the size of s is finite, you're welcome to think of pxy k as the xyth entry of the transition matrix raised to the kth power, right? Which I'm sure you've seen in 160A, but here we're going to write it this way. And just to connect things up a little bit in terms of how you calculate them, right? So I guess I want to write that, how do I get the pxyk's from the things that I'm actually given, which are the one-step transition probabilities? Well, let's try something a little bit more simple-minded, which is let's get the two-step transition probabilities. And here, this is where the Chapman-Kolmogorov equations come in handy. You sum right over, right? You have a trip that's of length 2. You stop halfway somewhere, and you use the one-step transition probabilities to get from x to z, sum over z, and get from z to y, right? So now you have, with the numbers that you're given, you know exactly how to compute the two-step transition probabilities, and this sum may be infinite, right? That's certainly a possibility. And in the case when S is finite, this is exactly the matrix multiplication that raises the transition matrix to the second power. And then, it should be clear how to recursively then get all of them, right? This is the three-step transition probability would be take the trip, and now I have the two-step, so I'm going to split the trip into two steps, px to z in two steps, and then I'm going to wrap up the trip in the last remaining step, right? So this is Chapman-Kolmogorov for a trip of length 3, and so on and so on and so forth, until you get to to k. So now you know how to, at least in terms of computation, you know how to get from what you're given to any px, y, k, at least in theory. And then we're going to take the limit, and so you got to kind of think, what is this trying to tell us? So, in the last lemma, let's just take a step back for a second. In the previous lemma, we had this statement that once a Markov chain enters its stationary distribution, it stays there forever. Right? And the fact that it got there, and that was at this magical time m, that was not specified how, right? It just kind of happened, right? We just sort of supposed it happens. Here, what we're trying to do is to say, well, what if it doesn't happen, right? What do the probabilities converge to at all, right? Let's just, maybe they don't even converge to anything, but let's suppose that they do converge to something, right? And we're going to label that something as alpha, right? So in essence, what we're saying is there's going to be some distribution that this Markov chain is going to find after searching for an infinite amount of time. It's going to run for an infinite amount of time and then end up in some alpha, right? And maybe that's not true at all, right? Maybe there'll be, in fact, there are examples where that's not true. There are examples where it doesn't converge to anything at all, but there are also examples where it does, so we're thinking of those chains, right? The chains that actually converge to something. And the important part here is that the alpha does not depend on the starting point x, right? It's the same exact alpha for every single x here, right? Regardless of the starting point, the convergence leads us to something that does not remember the initial state, and that that part is I guess a little bit reasonable, right? From what we know about Markov chains already, they did not have a great memory, and so they kind of just look at where am I now? I'm gonna behave only based on where I am present, right? And never look all the way back. So it's certainly reasonable that after a long amount of time, if this limit exists at all, it would not care about what x, like where the chain came from, right? It could have started from here and ran, right, and we could have started from somewhere here, and we ran it, right. It ends up in the same place, and that place is alpha. And so now you've probably kind of checked ahead. The conclusion is that alpha y is going to have to be the stationary distribution, right? Alpha is going to have to match the stationary distribution. And so what's the big takeaway? The takeaway is that if this chain converges to any kind of distribution, right? If it gets to any meaningful equilibrium, that equilibrium is going to be described by the stationary distribution, which we know, we know how to characterize it, right? It has those global balance equations assigned to it, right? So it's not going to be any other limit, right? If there is a limit, it's going to be the equilibrium, right? The stationary distribution or the equilibrium distribution of that particular Markov chain. So think about kind of through what that means. There's a lot to digest in the statement of this lemma, but the proof is kind of short as long as we're willing to be maybe a little bit careless. So one, there are two steps essentially, right? The first step is something that looks very much like the global balance equations, but it's going to be extended to the k-step transition probability, right, for all k. And so for k equals 1, that is literally the definition of the stationary distribution, right? Those are the global balance equations when k equals 1, but it's maybe not as clear why that would be true for k equals 2 and otherwise, right? And so we'll prove step 1, but it seems reasonable, right, that would hold, right? But we'll prove it. Let's for now assume that step 1 is true. We're going to take this statement as given. The next thing to do is to then take the limit. So what limit? Let me add k to infinity. That's the limit that I'm thinking about. And we need to do this very carefully, right? So I'm going to put carefully in parentheses, and I guess at first I'm going to do it quite carelessly, and we'll come back to why I'm saying carefully. So I'm going to start with 1, and I'm going to take the limit as k goes to infinity. If I do it on the left side doesn't depend on k, so the limit is just pi y, right? Pi y, take the limit as k goes to infinity, remains pi y. On the right-hand side, and this is where I meant carefully, it's not necessarily going to be all that easy to just put that limit into the sum, right? If that sum is infinite, which it could be, we're not really justified in doing that, at least not right now. If s is finite, then it's perfectly fine, right? So it's a big difference between finite state Markov chains and infinite state ones. But let's suppose, for now, that I can actually take that limit, and so the limit goes in, it slides right past the pi x, and it gets to this, and applying what we're given turns into alpha y. And then hopefully you can see this last step here, right? That's just recognizing that alpha y doesn't depend on x, so it comes out of the sum, and the sum of any distribution, including a stationary distribution, is always 1, right? So that's how you get the very last step. So that was a quick thing, but it's not not that easy to realize sort of how to put all these pieces together. I mean, you clearly have to try to get the pxyk in there somewhere and try to relate it to the pi and so on. So this this lemma sort of I got this from Ross, or I got the idea of it from Ross, and you can find this chapter 4, I think it's page 220 but it's certainly chapter 4, so just search that PDF. This is the 11th edition from 2014, and you'll find it, and he does something similar but also different. And I think in Ross's case, there is no easy justification for exchanging the limit and the sum, and so I'm not necessarily following the same exact proof. Hopefully this what we have here is going to be a little bit better, right? So first of all, it's shorter, I think, and then second, we're going to be able to justify the exchange of the sum and the limit for those of you who are interested in kind of those mathematical details that should be of interest. But in terms of the kind of the careless proof, if we're willing to claim 1 and we're willing to kind of put that limit inside the sum, we're done, right? And the takeaway is sort of a kind of a major realization that if the distribution of the chain approaches approaches some limit, that limit's going to be the stationary distribution. Right. Okay, so I guess maybe before, I want to maybe pause this clip and then handle both of these items separately to get a bit more board space, but perhaps here what I could do is give you some a little bit of a hint as to why exchanging these limits has to be done carefully. So this really comes down to kind of what are called double sequences. So the first thing to do when you have kind of something like this, and what we really have is really this, right? It's the limit as k goes to infinity of a sum that's potentially infinite, or over infinitely many terms, pi x p x y k. So this is what we have, and the question is how do you handle this? So the first thing to do is to try to make the sum finite, and for that I need to be able to enumerate these elements. So because the s is discrete, here's a trick that you may like or use at some point, whenever your set is discrete, or in other words countable, you can enumerate its elements like this. So all I'm writing here is just a possibly infinite but countable or discrete collection of sets of states that in the end is equal to my state space S. And the reason I enumerated like them is that now I can take that sum above and write it as from I equals 1 to n pi of xi, probability of x I y in k steps, right? So all I've changed here is I've changed the sum over all states labeled by x to a sum that's first of all finite, right? It goes up to n, and I'm slowly enumerating all of these states xi, x1, x2, x3 all the way, right? And all of them together going to infinity will enumerate my entire state space S. Right, so this is x, I, y. And this is now, you can think of it as a function of n and also a function of k. And in that sense, it's a double sequence, right? And so the question is now, kind of, can we exchange limits rather than sums, rather than a limit and a sum? And so you now have k to infinity, then limit as n goes to infinity, right? So this first limit is k goes to infinity, the second limit is n goes to infinity, of f of n k, right? And the question now becomes, can I interchange the two, in which case the limit as k goes to infinity goes into here, right? And the second limit will take care of the sum, restoring it back to this infinite one. So that's gonna, I mean, maybe let's look at that in the next clip to make sure I have some board space. But to convince you that it's not, you shouldn't be just kind of flipping these two willy-nilly, right? It's the, like an example would be, consider the sequence n over k plus n, right? Now, if you take this limit, depends on which limit you take first, right? So if you take the limit as k goes to infinity first, you'll get 0. But if you take the limit as n goes to infinity first, you'll get 1, right? And so following it with the second limit is not going to do much, right? And you're kind of out of luck, right? So that's the reason for why one has to be careful. And we just showed an example where it totally screws up, so we can't really conclude any of this. And so in the next clip, we'll kind of dig into a little bit more detail behind items 1 and 2.